Swayam Prabha. Digital India. Educated India.
So, good afternoon. I think you had a interesting 1.5 day session so far on this course on multiphase heat transfer, and so far it has been mostly focused on the basics of different kinds of transport phenomena, thermodynamics, and then focusing on governing equations of mass, momentum and energy. And today morning you had some session where multiphase flows were introduced, classification of different types of multiphase flows, how do you deal with dispersed multiphase flows versus separated multiphase flows, and particularly more focus on the dispersed multiphase flows in terms of how do you model, for example, so you look at the mass, momentum and energy exchange between the continuous phase and the dispersed phase by accounting for several interaction terms. So, now what we will do is in this session we will look at phase change heat transfer. So, you talked about you were looking into how mass, momentum and energy exchange happens between two phases. So, and he also showed that under what conditions that mass and energy exchange happens. Momentum exchange can happen even when there is no heat transfer, because you can have a dispersed phase or even two phases which can actually have drag interaction, buoyancy force interaction and so on. But when the specifically mass interaction and energy interaction happens when there is a phase change. Okay. So, phase change is primarily the most important contribution to mass and energy interaction, because there is a change of mass from one phase and you are adding that to another phase and vice versa, and associated with that is an energy exchange. So, you are basically taking latent heat of vaporization from one state, you are deducting it so that the energy, the sensible energy also can come down along with that. So, accordingly there is an energy interaction between the two phases. So, as he said, when you are talking about phase change, this is going to be important, and also when there are chemical reactions, also there is a species formation, so which can result in interaction of mass and energy. So, what we will look at in today's session briefly, first is we will look at phase change heat transfer in terms of pool boiling and condensation. So, these are very basic phase change heat transport process. Then we will look at extension to pool boiling, which is called the convective boiling or the flow boiling, and we will look at flow boiling in conventional size channels as well as in mini or micro channels, and some illustrative research examples I can give you from our own lab in doing this kind of sophisticated experiments. I think the very first thing that you need to understand, of course, this is a slide which shows what is the difference between boiling and condensation. So, when you talk about boiling, it is basically a phase change from liquid to vapor state, and this can happen only when the liquid is reached its saturation temperature at a given pressure or above the saturation temperature, right. So, this is basically the process that we all see in everyday life when you probably heat a pool of liquid in a pan, so you boil water and you generally see that you wait initially for some time, you do not see anything happening, you just see that everything is stationary, but what is happening inside is there is some kind of convection that is taking place. Okay. So, that is basically called the natural or free convection, and once the heating goes on for some more time, slowly you start seeing what is the first important change that you see within the boiling process. You start seeing slowly some bubbles are nucleating at the surface of the heater and the liquid, and then as you continue heating this, add more heat to the fluid, you see these bubbles are basically growing in size, and not only they are just growing, they are also detaching from the heater surface by means of buoyancy, and then they rise up till the surface of the liquid and the surrounding vapor. So, depending on the amount of heat that you put in, so this kind of nucleation and detachment of these bubbles can happen continuously, and they can happen more vigorously also. If you continue to add more and more heat, you see that this bubbling process is more rigorous, and at some point which you generally do not go in a normal household application, you just stop when this bubbling happens and you close the thing. But if you do it in a controlled experimental lab, you can also go to a temperature which can actually exceed the or close to the melting point of the metal at high heat fluxes. So, this is in a completely different regime of boiling. So, we will see all these phenomena, but boiling is a very practical process. You observe this in your household applications everywhere, okay. And of course, people have mastered boiling, especially when it comes to cooking, because we know how things basically cook. You use also a pressure cooker basically, so that you can enhance your boiling process more efficiently in cooking your food. So, the applications of boiling are numerous. So, why do we prefer boiling over conventional heat transfer modes? So, you have all the single phase heat transfer modes that Professor Marco covered, including conduction and single phase convection and radiation, but there is something very special about boiling or any phase change heat transfer, because the heat transfer coefficients are at least 2 or 3 orders of magnitude higher than your normal single phase convective process. So, even in pool boiling is not actually a convective process in the sense. So, you are not basically causing any bulk motion of the fluid, but you have natural convection and then you have this boiling phenomena. Even there you have a very high significant improvement in the heat transfer coefficient of boiling. So, therefore, wherever you want to improve convective heat transfer processes, so boiling is most preferred mechanism. So, you do not want to just be satisfied using single phase heat transfer as the mechanism for removing heat, because there is a limitation. If you are using air, because of the low thermal conductivity and heat capacity and Prandtl number, you have very limited values of H that you can extract. If you go to using liquids, it will be slightly better, but again there is a upper limit. So, ideally you want to make use of phase change heat transfer as the most important mechanism for heat dissipation. So, cooling systems is the number one application of where boiling can be used, and of course any industrial process, whether it is power generation or refrigeration cycles, you see phase change heat transfer being employed. So, if you look at power generation, you have in your conventional Rankine cycle you have an economizer, you have a boiler. So, economizer is mostly sensible heat addition, but boiler you have basically phase change happening. So, your saturated liquid is converted into vapor, and again when it comes to condensation, it is just the opposite effect. There is a phase change happening, but it is converting vapor to liquid, and vapor cools below its saturation temperature. So, when you have a substrate or a surface which is below the saturation temperature of vapor, then the vapor cools and it converts its phase from a vapor to a liquid state. So, that is the only, because yesterday Marco was talking about the phase stability, phase transition, so metastable states. So, these are all basically constrained by thermodynamic processes. So, you cannot change them. So, if the water has to be changing phase, it has to change the phase when you bring the substrate temperature below 100 degrees at 1 atmosphere. So, this is the characteristic that it has to follow to respect the thermodynamic phase transition diagrams. So, similarly the applications of condensation are everywhere. Number one is in steam power plants, you have a condenser, because the vapor has to condense again to liquid, and you have to have a closed system, because you do not just take water from outside and then heat it and then dump it out. You have to again condense it back, again send it to the pump and then back to the economizer or the boiler. Now, also you have HVAC systems, heating, venting, air conditioning systems. They all follow refrigeration cycles. So, in whether it is a vapor compression or vapor absorption system. So, you have essentially there also you have a evaporator and a condenser. So, therefore, boiling and condensation process are inevitable. They are used, if you look at boiling process, as far as electronics cooling is concerned, cooling systems, it is very efficient because of its high heat transfer coefficient, and it is also used in cycles in industrial processes in power generation and refrigeration. So, both boiling and condensation are used, and here you can see a very nice figure where in a lab, I think this is from MIT. So, they have done a very controlled experiment of boiling, and you can see very large bubbles being nucleated and they are all merging. It is almost about to transition to a film boiling case, but you do not see individual bubbles anymore, but you can see there are so many bubbles nucleating, they are growing rapidly and then they are merging, and then you see big vapor pockets coming out, you know. So, we will talk about this phenomena little later. Similarly, condensation, when you look at condensation, I think in everyday life you also see this. For example, when you have a outdoor condition where probably it is very hot, okay, and it is very humid, and then inside you turn on the AC to maybe 17-18 degrees and then you have a window pane. So, generally what happens, slowly you start seeing the water vapor in the atmosphere is condensing on the window pane, and you see these water droplets are collecting. So, that is because, you know, locally at the window pane your temperature is less than the dew point temperature, because it is not just a single component vapor outside. You know, you should understand that in real life there is nothing like there is only one water vapor, it is also a mixture of water vapor plus atmosphere. So, as far as water vapor in the mixture of vapor and atmosphere is concerned, dew point temperature is more important than saturation temperature, because it is only water vapor is only a fraction of the entire atmospheric pressure. So, you have to look at what is the partial pressure of water vapor and look at what is the corresponding saturation temperature at that partial pressure, that is your dew point temperature. So, if your atmosphere is saturated with let us say water vapor, the relative humidity is 100%, then the dew point temperature will be very close to your saturation temperature corresponding to the saturation pressure, because the air is saturated. It does not mean this is 100 degrees, because you know such saturation pressure of water vapor at that particular temperature will be limited. So, you have to look at the tables. If it is 30, for example, if it is 30 degree, the saturation pressure may be something like 0.03 bar or 0.04 bar. So, at 0.04 bar, so that is 30 degrees your dew point temperature. So, if your local temperature falls below 30 degrees, then if your atmosphere is completely saturated with water vapor, all this is going to condense. So, you will see this formation of water droplets nicely on the mirror or glass surface, right. This is something that you see, even people who wear glasses, they can see. You are sitting in a car where AC is turned on and suddenly you come out, you will see frost, that is nothing but condensation happening, okay. Anyway, so another important thing when we talk about boiling is you have to understand technically as a heat transfer person, what is the difference between evaporation and boiling, because we usually interchange evaporation and boiling in day to day life. We try to refer to the same thing, and even heat transfer engineers like me, we also interchangeably use evaporation and boiling, but then there is a very subtle difference. So, evaporation is something that occurs at the liquid vapor interface, okay. So, this is clear, but then what is the driving potential for this evaporation? It is not temperature difference, but it is concentration difference. So, the evaporation happens because if you are looking at, let us say, the mole concentration of water vapor right at the interface of the liquid, and so this is completely saturated, right. So, this is XH2O saturated. That means you know what is the partial pressure, what is the saturation pressure of water vapor corresponding the temperature, let us say it is at 20 degrees. So, if it is 20 degree, it may be something like 0.03 bar, right. So, this is your condition at the interface. Now, surrounding that you have, depending on the relative humidity of you know air. So, if suppose your relative humidity is 80%, so accordingly your air is basically having 80% or 0.8 times basically your Psat of H2O at 20 degrees, okay. So, in this case it is something like 0.02 or 0.03 0.02 bar. So, now you have a partial pressure difference of 0.03 minus 0.02 bar existing at the interface and just above the interface where you have the surrounding vapor. So, this partial pressure difference is the driving potential for evaporation. So, you see this entire system is isothermal, everything is at 20 degrees, there is hardly any temperature difference, but there is a concentration difference existing because at the interface of the liquid vapor it is saturated with water molecules, and just outside because of the relative humidity. So, your partial pressure of water vapor is slightly lower than the saturation pressure depending on the relative humidity. If it is 80%, so it is 0.8 times your 0.03 bar, which is around 0.024. Okay. So, this pressure difference, this partial pressure difference is related to the concentration gradient, right, because when we write down the equation of state, we are assuming, let us say, at 1 atmosphere water vapor can be treated as an ideal gas. So, you have PV is equal to nRUT, this is the universal gas constant, this is the number of moles and this is the volume. So, therefore, your N by V is basically your molar concentration, let us say, and that is given by your P by RUT, right. So, therefore, at a given temperature, let us say temperature is held isothermal at 20 degrees, your molar concentration is nothing but a function of your partial pressure. This is the partial pressure of water vapor, right. You can also write in terms of mass concentration. So, molar concentration counts how many number of moles in a given volume. Mass concentration, you can convert that into equivalent mass per unit volume by multiplying and dividing by the molar mass, this into MW, this is your total mass. So, then instead of x you can use what is called as a mass concentration Y, which is basically M divided by V. So, generally we use for mole concentration, we use the symbol, it is chi, it is actually a Greek symbol, but some people use x. So, this is used to define mass concentration M by V. So, in any case, the idea here is when you talk about either mole concentration or mass concentration, it is a function of the partial pressure, okay, if you use the ideal gas equation of state. So, generally, therefore, evaporation is something phenomena that can happen completely at isothermal conditions. You do not need any driving temperature difference, it is only driven by concentration difference or partial pressure difference. And I gave you the example now, depending on the relative humidity, how this driving potential is created. If your air is completely saturated with water vapor, then there is no gradient of concentration, and therefore there is no evaporation. So, that is why you see in very high humid situations, like in Chennai when it rains, the air is nearly saturated, 95% relative humidity, and you have wet clothes, you hang, it never dries, you have to wait for a very, very long time. Whereas in a dry weather, in a relative humidity of 40 or 50%, within half an hour everything dries up. So, that is due to evaporation, and the cooling that it produces is called evaporative cooling. So, evaporation is not just a mass transfer, the molecules are not just converting from a liquid state to vapor state. So, associated with that there is an energy that it is taking away from the liquid state in order to become a vapor state. Okay. So, it is taking the latent heat of vaporization as the energy that is required to convert, because you need to supply energy to convert from a liquid molecule to a gas molecule, and that energy comes from the bulk of the liquid, and in the process what happens, the temperature of the liquid also reduces. So, this is called evaporative cooling. So, evaporative cooling is used in a lot of applications. Practically when you are probably walking or exercising and you are having sweat, the one of the easiest mechanism for the body to lose heat is through evaporative cooling, and on humid days when you cannot make use of this mechanism, you feel that you are not very comfortable. And also people use this evaporative cooling in desert coolers, for example. They spray water onto a fan, and then if the relative humidity is very low, due to the evaporation of these water droplets, locally the air gets cooled because it is taking the heat from the air to convert from a liquid state to a vapor state, and in the process locally the air is cooled. So that is the evaporative cooling effect. Now as far as boiling is concerned, it happens not just at the liquid vapor interface but at the solid liquid interface. So as I told you, you have a container of water. So the boiling is something that you observe where you supply heat to the surface at the interface between the heater and the liquid. So of course there is some evaporation happening here, but the boiling that we are referring to is the nucleation of bubbles that you see at the heater and liquid. So that is the boiling process, and what is the driver for this boiling? It is essentially temperature gradient. Okay. So you do not if you do not have temperature gradient, you do not have boiling, it's period. Whereas evaporation can happen even without temperature gradient. You keep a drop of water on this table now, and the water is isothermal with surrounding, and the table is also isothermal, but even then after 1 hour you will see the water droplet is evaporated. So it is only driven primarily by the concentration gradient, and of course if you have a heated surface, it is going to augment this evaporation process, right, because what happens? So why does the heated surface augment the evaporation process, although it is primarily driven by concentration gradient? The saturation pressure is a function of the temperature. If you are raising the temperature of the substrate, the saturation pressure goes up, thereby the concentration gradient increases. So the same outside temperature of 20 degree, if I heat my wall and raise it to say 60 degree, my evaporation will be more rigorous because locally my saturation pressure is higher at the interface of the liquid and the vapor. Okay. So that is going to increase the concentration gradient, and that will promote evaporation process. So although evaporation process is affected of course by a temperature difference, so it is affecting it through the Clausius-Clapeyron equation, so which is basically relating the saturation temperature to the pressure, right, and not directly, whereas boiling is completely influenced only by temperature difference. And when we classify boiling, we talk about two kinds of boiling phenomena. One that I was just explaining, when you fill water in a container and you heat it, okay. So that is called the pool boiling, because there is no bulk flow. You do not actually pass the fluid in a tube or something, but it is just a container, and the container is itself, boiling is taking place within this stationary pool of liquid. This is called as pool boiling because there is an absence of bulk fluid flow. So any motion of fluid that can happen here is only due to natural convection, because before the nucleation itself starts, you have a natural convection due to the density difference of the fluid close to the heater and away from the heater, and that buoyancy process will be there always in the background. It is not just the natural convection is just gone, but that convection will be much smaller than the actual convection induced due to the nucleation and detachment of these bubbles. So these bubbles, so how are they improving the convective characteristics during boiling? So these bubbles, you see, they are all forming, they are nucleating, they are growing. So as they are separating, what happens is there is a fresh pool of colder liquid that has to fill to basically replenish the volume in which the bubble has just disappeared. So as the bubble is leaving, there is a fresh pool of liquid that is entraining. This is called rewetting. So it has to rewet the surface, and in the process there is a convection all the time happening, So this bubble is actually leaving, so there is a fresh pool of liquid coming and rewetting, and in turn that will also get heated up, and again there is a bubble that is forming there. So there are two processes here. One, this is a micro convection. So whatever you see here, the rewetting phenomena is actually a micro convection. So this is happening just at the vicinity of the bubble and the heater surface. It is a local phenomena, and along with that, now this cannot be the only mechanism by which your heat transfer coefficient can increase by 2 orders of magnitude, right. So what is the other important mechanism by which the heat transfer rate augments?
Creating more continuous.
This is a part of, okay, you have a phase change, because primarily what is happening, you are supplying heat and all that heat is now used to supply a latent heat of vaporization to convert the liquid to vapor, and all that heat is going into that mode of heat supply. So, you have sensible heat, you have latent heat. Now, phase change heat transfer process basically utilizes the latent heat mode. So, especially if you have water, water has a very large latent heat of vaporization. So, whatever you supply, it goes only in phase change mechanism, and therefore, the heat transfer rates can be very, very high, because it especially with using water which has a very large latent heat of vaporization. So, there are two mechanisms. One is the micro convection that we are discussing, that is only a small contribution, it is not a major contribution, but the major contribution is the use of latent heat of vaporization. Okay. Now, so this pool boiling is something that is very fundamental for understanding. We will quickly go through that. I am sure most of you have some knowledge. Then there is another boiling mechanism where you also have to come across situations like heat exchangers in power plants or any cyclic process. You cannot have a stationary pool of liquid and then just observe boiling. So, you have to also circulate the liquid through the heat exchanger tubes, and therefore, this becomes what is called as the flow boiling. So, for example, you have these kind of tubes, so you have circular tubes for example, and you are pushing flow through these tubes, and along with the flow, this is a convective motion, along with the convective motion you also have a phase change, because locally you are heating the fluid above its saturation temperature. So, there is also a boiling. So, boiling plus convection together is called the flow boiling process. So, in pool boiling you are primarily making use of micro convection plus of course latent heat of vaporization, whereas in flow boiling there is also an added effect of convection, which is your macro, not micro convection. This is the bulk motion plus of course your latent heat of vaporization. So, now you can imagine that your flow boiling will be much more effective than pool boiling in augmenting your heat transfer coefficients, because you are not just using only the latent heat of vaporization, but also certain things are happening when there is a bulk motion of the fluid. So, we will see what are those things, and then this is a very nice of course as it comes to any forced convection mechanism, you need an external pump to drive this. So, that is one difference. If you use for example boiling water reactors and so on, where probably these nuclear fuel bundles are suspended inside a pool of liquid, there you may expect pool boiling to happen. But in most of the heat exchangers, when there is a closed cycle heat exchanger, you always have a active flow loop by using a pump, and then you see flow boiling is happening. Now, this is a very interesting picture from European Space Agency. So, they conduct these kind of missions called parabolic flight tests, where they fly an airplane under different accelerations. So, they have negative acceleration, then 0 g and a positive acceleration. So, then they study different gravity, different acceleration due to gravity. What is the experiment on flow boiling or pool boiling, how does these bubbles look like. So, for example, in this case there was a pool boiling setup carried on in a parabolic flight, and it undergoes multiple accelerations, and you see normal 1 g condition on earth. So, this is the kind of bubbles, you see these bubbles are nucleating and they are just going and then followed by some smaller bubbles at the back. Now, once you go to 0 g, what happens is completely different in terms of boiling process. In large extent, if you look at pool boiling, these bubbles are nucleating, growing, and then they detach. And the detaching process is primarily driven by buoyancy, okay, and this is more prominently seen when you have 1 g environment. Okay. Now, if you go to 0 g or in microgravity where there is hardly any buoyancy force, then there is nothing to detach. So, what happens is these bubbles keep growing till they become very, very large, and then maybe at some point they detach because of some other instability or some perturbation, but by themselves there is no buoyancy to detach. Now, what you see in these kind of tubes is some of these bubbles are become so large, they fill the entire diameter of the tubes, and then they have to keep moving on because of the convective motion. But in pool boiling case, you will find that these bubbles become very large and hardly they even detach. Now this also to some extent is seen in smaller gravity conditions like Moon or Mars, but 0 g is an extreme case where you hardly have any buoyancy forces for detachment. So buoyancy forces are required, therefore 1 g environment is probably what you see under Earth. You see bubbles nucleating and departing, they are detached and they depart, and plus there is a convective motion. Whereas in 0 g case, the detachment of the bubbles does not happen by itself, it is mostly pushed by the flow. So you see, therefore these are very nice shaped larger bubbles which are actually can become equal to the entire diameter of the tube before they are pushed by the flow itself. Again, we classify boiling based on what is the temperature of the fluid when we start this boiling process.
What are the applications for 0 g case?
0 g is typically, when you are doing see fundamentally it is mostly understanding the physics of boiling under different gravity conditions. Second thing is when you are designing this kind of boiling based heat transfer process in spacecraft cooling, spacecraft thermal management, say whether you use pool boiling or flow boiling systems. So you need to understand how they are going to perform at reduced gravity comparing to terrestrial gravity conditions. At room conditions, you may see an excellent performance of your system, but once it goes there, you may see that the system is hardly moving, because the bubbles are all just blocking and there is nothing moving. So in that case, you have to understand the fundamentals of this. Okay. So depending on what is the temperature of your water when you start this boiling process, if you are keeping the water below the saturation temperature, that is the bulk of the fluid is below the saturation temperature while the substrate is heated above the saturation, this is called subcooled pool boiling. This is a pool boiling case. You can also extrapolate it to flow boiling, and in case your entire water is exactly kept at saturation temperature and your surface is heated above the saturation temperature, this is called saturated boiling. So you have to understand that subcooled boiling and saturated boiling can produce completely different boiling mechanisms, because in the case of subcooled boiling, the boiling is initiated right at the interface of the solid and the liquid in terms of these large bubbles, which then have to rise, okay, as you keep increasing the heater temperature up, and then as you go up, the temperature of the bulk liquid is much lower than saturation. It does not promote a state where the bubble can remain in vapor state, they again collapse. So they cannot reach all the way up to the liquid vapor interface. Whereas in the case of saturated boiling, you will see there are two types of nucleation. One is, this is called the heterogeneous nucleation, right. So why do we call this as heterogeneous? Because this is happening at the interface of a solid and the liquid, and whereas here, because locally the temperature is above the saturation temperature, you can also have pockets of vapor that can happen due to evaporation, which is called homogeneous nucleation. So when you have a saturated boiling, in this case homogeneous nucleation also can happen. So you will have more vapor pockets everywhere within the fluid. Apart from the nucleation that is happening at the interface, you can also have vapor pockets spread all around your fluid, and you will see to some extent there is more nucleation of vapor pockets also in the liquid side. Now let us quickly go through this pool boiling curve. So this was actually considered one of the most fundamental and groundbreaking experiments as far as boiling heat transfer is concerned, and this was done in a saturated boiling condition. That means the liquid is at saturation temperature, and then you have a heater which is like a wire, some kind of a nichrome wire or whatever it is, and you supply a power directly, a DC power to this heater wire, and in the process the wire gets heated and the surrounding fluid also gets heated. Okay. So, so this is the kind of experimental setup. It looks quite simple, and it was first done by Nukiyama. He is a Japanese scientist in the early part of 20th century, and this boiling curve is named in honor of Nukiyama as the Nukiyama boiling curve. So, what he did was he used a power controlled heating, that means he was able to control how much heat flux he is supplying to the wire, nichrome wire, rather than controlling the temperature of the wire. So, this boiling curve can be obtained in both ways, either you can control the power, you can plot the boiling curve. So, which involves plotting the heat flux that you are measuring or supplying to the heater as a function of what is called as the excess temperature difference. So, this is the temperature of the wire or the surface temperature minus the saturation temperature. So, in the case where you are doing a power controlled heating, you are basically supplying a fixed amount of heat flux, and what you are doing is you are measuring the temperature of the heater surface, okay, and you are plotting this excess temperature. In the case where you are doing a controlled temperature experiment, you can actually maintain the temperature of this heater to a set value, and you can measure what is the corresponding heat flux, and you plot a different set of curve. So, originally he did this experiment with power controlled heating, and when he plotted this curve, he got a very interesting curve. So, initially in a regime till here about 5 or 6 degrees of excess temperature above the saturation, there was nothing, no bubble nucleation, nothing happening. It was primarily natural convection dominant. There is a temperature difference of hardly 4-5 degrees between the heater and the surrounding liquid, and that is only sufficient to cause natural convection currents like this, and there was some convection, but it is not a very powerful. So, you see the heat flux is slightly increasing along with the surface temperature. Now, at some temperature which is called the onset of nucleate boiling, so which happens at around 6 degrees, 5 or 6 degrees for water at 1 atmosphere. So, he started seeing nucleation of small bubbles or vapor pockets, and as he continued to increase the power supply to the heater, you see that these vapor pockets becoming larger in size, and then slowly they are detaching and they are moving up due to buoyancy, and you have a regime where when you increase your heat flux continuously, your excess temperature or the surface temperature of the heater also continuously increases, okay. So, and it reaches a maximum point. So, it is not hypothetically continuously increasing forever. So, it reaches a maximum point, and beyond which if he increases the heat input a little bit more, so it directly goes to a very large surface temperature. So, this is actually going to lead to such a dramatic increase, so that you can see this is actually plotted in a log scale. So, maybe at the point where it is a maximum heat flux, which is called the critical heat flux, you have 30 degree superheat. From 30 degree it goes to 1000 degrees. So, which is close to the melting temperature of the nichrome wire, and if you just continue heating, the heater is going to completely melt and fail, okay. So, now therefore, he was surprised that such a small change in the heat flux beyond the critical heat flux has completely changed the surface temperature to such a large extent, resulting in the failure of your heater, and therefore, there is something happening here. And of course, visually he could see that those nucleating bubbles have become much larger, to the extent that there is a thick film of vapor completely coating the heater surface. So, there was a vapor blanket. So, this mode of heat transfer he referred to as film boiling, okay. And the more benign mode, which is actually more useful as far as boiling heat transfer mechanism is concerned, so that is called the nucleate boiling. So, therefore, you should understand the difference between what is benign and what you are essentially seeking for is basically operating in a controlled manner where only nucleation happens, and the other extreme is where an uncontrolled heating happens, which is the film boiling, where there is a very thick film of vapor blanket, and because of which vapor has very poor thermal conductivity. So, there is hardly any phase change process happening there, but rather there is hardly any phase change process happening, but it is only by means of conduction that there is a heat transfer happening from the heater, and that too against a very poor thermal conductivity medium. So, because of which what happens is you will see the actual heat flux should be dropping, but when you do a controlled heat flux experiment you cannot achieve this dotted regime. So, you directly go from the critical heat flux to this point, by the time it is too late. Okay. But if you do a controlled temperature experiment where you maintain the temperature and you do it, you will be actually even go through this dotted line. But now once you reach this point where your burnout is happening and you realize that you are burning out, and then immediately cut down the heat flux or reduce the heat flux, you will have an hysteresis. Now you are not going to come back like this. Okay. You will be coming down the heat flux. As you reduce the heat flux, your temperature is going to gradually come down, and then it reaches a minimum heat flux around say 100 or 200 degrees superheat. So that is called the Leidenfrost point. Okay. So the minimum heat flux. So therefore when you are doing this with a controlled heat flux experiment, your curve will be, as you increase the heat flux, it goes till the critical heat flux, a little bit more increase is going to go to this burnout stage, and once you realize and then slowly reduce the heat input, it is again going to come down in this path, not the way that you came up, but it is going to go down like this and then reach a minimum heat flux, and from there if you reduce the heat flux a little bit more, it is going to come down directly to this point and then come down. So this is a very unusual way of obtaining this pool boiling curve, but this is what was observed by Nukiyama. So that is why if you just look at the experimental setup, initially you may just imagine that such a simple experiment, so you should be getting this curve. So why did he do so much of research on this? But then if you really understand the subtleties, there is so much happening, because the initial part of the heating curve is in one direction, the cooling curve is going in another direction, and finally he has to extrapolate or interpolate between the heating and cooling curves to get this particular dotted line, which is what is happening in the transition from the nucleate to the film boiling. So you may ask, okay, so when I have this vapor blanket, it is going to deteriorate the boiling heat transfer. So what causes then the further increase in the heat flux? So this is attributed to radiation, because you see the temperatures, excess temperatures are already hundreds of Kelvin. So radiation becomes the most important mechanism for heat transfer and not phase change. Okay. To that extent, if you go almost to the melting point of the nichrome, so you see the values of the heat flux almost match the values that you obtain with phase change in nucleate boiling regime. So to that extent, the radiation becomes a very important contributor. So of course you do not want to burn your nichrome wire to get a very high radiation heat transfer, right. So what you are looking for is improving heat transfer in a more sensible manner by maintaining in a nucleate boiling regime, and therefore practical engineering applications you are always limited by the critical heat flux. You do not want to accidentally go beyond the critical heat flux. The reason why we should understand this boiling curve is basically, as a designer, when you are creating any design of heat exchangers, the flow rates and so on should be designed in such a manner that you are never going to exceed this critical heat flux, right. So therefore for that you need to know how to predict the critical heat flux for a given condition. Okay. So I think I have explained most of this process in a very concise manner, but of course when I share this PDF you can go over some of the details. So one more question that I think you should ask is that why does nucleation does not happen immediately after I exceed the saturation temperature. For example, at 1 atmosphere water saturation temperature is 100 degrees. Why does not nucleation happen at 100.1 degrees? Why does not it happen at 100.2, but rather it takes 5 or 6 degrees superheat for the onset of nucleate boiling? The answer to that again comes from thermodynamics. See, basically when you are talking about boiling, if you look at at very small scales, maybe a nano scale, if I have a roughness, so there is a vapor pocket that has to be created like this. This is a vapor pocket, So this is the surface, right? We are talking about a rough surface which has some kind of roughness elements, which is the, so where does these vapor pockets get created? They get created in these cavities where you have roughness. So therefore you can actually alter the nucleation characteristics by changing the surface characteristics, right. So now if this vapor has to be created and nucleated, assuming that now you have a small micro bubble that is going to be generated within a cavity, it has to satisfy your Laplace-Young equation. So this is your Laplace-Young, which gives you the mechanical equilibrium between the vapor and the surrounding liquid. So you have a vapor bubble, so there is a certain pressure inside, which is the vapor pressure. Outside you have the liquid pressure. Obviously these two pressures cannot be the same because the vapor is in a very stable state. So there is also a surface tension which is acting normal. So therefore the vapor pressure has to balance the cumulative effect of surrounding liquid pressure and the surface tension force. So that is given by the Laplace-Young equation. So in order to do that, so there has to be a pressure difference between the vapor and the surrounding liquid or surrounding fluid. So what happens is, inevitably, since the pressure inside is higher, the corresponding saturation temperature for the vapor to exist inside the bubble should also be higher, right. So that is given by the Clausius-Clapeyron equation. The relation between the pressure and the temperature is given by the Clausius-Clapeyron. So once you put the Clausius-Clapeyron, so this is your delta P that you want to maintain between a bubble and the surrounding, and then you use the Clausius-Clapeyron, you see that you can get the expression for what should be the corresponding temperature difference, because the Laplace-Young equation is only a mechanical equilibrium or it is a force balance. So you cannot inherently know what is the temperature difference from that. Then you use the Clausius-Clapeyron from thermodynamics, you combine that with the Laplace-Young, and then you get an equation which gives you the criteria for maintaining a temperature difference, and that temperature difference between the vapor and the liquid turns out to be inversely proportional to the diameter of or radius of this bubble. That means if you have a very small bubble, very small vapor cavity and a very small bubble, you need a very large excess temperature to cause the bubble to exist in that stable state, right. And as the size of these cavities become bigger, the amount of wall superheat that you require goes down. So this is basically the reason why there is a point where there is an onset of nucleate boiling which is above the saturation temperature and not exactly at saturation. So this happens typically if you calculate for the average surface roughness, if you calculate for the smallest bubble, which is of the order of a micron or even smaller than a micron, this temperature difference for water comes out to be around 5 or 6 degrees superheat. Okay. So this point is called the onset of nucleate boiling. So I hope now you understand the reason why you do not get exactly at the saturation temperature. Now okay, now there are also some kind of understanding from these pool boiling experiments about there are some more mechanisms, like how is the diameter of this bubble when it departs from the surface. So there is a nucleation of the bubble, then there is a detachment of this bubble, and these bubbles keep rising up. So how do we calculate the diameter when it departs? So this is you looked at by different people, and there are primarily 4 forces which are acting on the bubble. So at the time you are talking about the bubble which is still nucleating, you have a surface tension, okay, and the time when it is about to grow and detach, you have basically buoyancy and drag force. So the buoyancy and drag forces, these are forces which are going to detach the bubble from the surface. These are attempting to detach because they are acting in an upward direction, and the surface tension and the liquid inertia are basically preventing the bubble from detaching. So essentially this is a balance between these two forces, the upward forces and downward forces. So for example, when you want to calculate what is the average size of this bubble when it departs, so you have to balance the buoyancy force with the surface tension force, because the buoyancy is trying to detach it, the surface tension is trying to hold it. So therefore if you do that balance, I think Fritz first in 1935 he came up with this classical equation for calculating the bubble departure diameter, and from there you can also estimate what is the velocity of this bubble when it rises up. Now apart from the bubble departure diameter, you also want to know what is the rate at which these bubbles depart. So whether there is only one bubble departing in 1 second, or there are the hundreds of bubbles departing in 1 second. So these are also given by some kind of a empirical model. For example, you need to know what is the there are two time scales that are involved. One is the delay period. First, for example, once the bubble grows, there is a certain time that it takes for the bubble to grow. So depending on the gravity, right, as I told you, on 0 g it is going to grow forever, whereas in earth gravity or hypergravity it is going to grow very quickly, and then so therefore the new bubble grows for a certain time Tg, and then once this bubble leaves, then you have the cold surrounding fluid which is basically re-wetting, and again it takes some time for this bubble to get heated up to reach the saturation temperature, right. So therefore there is another time which is called the delay period. So your final time will be a combination of basically your bubble growth time Tg and the waiting time Tw. So the inverse of this will give you what is the average departure frequency. So the bubble leaving and then the next bubble which is also leaving, what is the frequency between these two bubbles. So that is given by 1 over Tw plus Tg. This is called the frequency of bubble departure. And there were some experiments people have done, and people like Jacob in the late 1950s and Zubair, they have come out with a correlation where they said the product of bubble departure frequency and the bubble departure diameter is basically given by this expression. So it depends only on the fluid properties, so it is a constant. So once you know the expression for the bubble departure diameter, you can substitute into this and calculate the bubble departure frequency. So these two are basically the fundamental things that you need to understand in nucleate boiling. So some of the models that you have in pool boiling, in nucleate boiling, also involve these kind of empirical models where the bubble nucleation diameter and frequency are estimated. Okay, so I think I have talked about the nucleate boiling in some detail, but you can always go through it. As I said, the heat transfer coefficients can range from 2000 watt per meter square Kelvin to up to 30,000 watt per meter square Kelvin, which is very large compared to single phase convective heat transfer coefficients, which come to the order of few tens to a maximum of 100 watt per meter square Kelvin. Okay. So film boiling, as I said, so this is something that you do not want to stumble upon when you design your flow boiling devices, but as a fundamental understanding you need to know the point, the critical heat flux beyond which further increase in the heat can actually lead to the unstable state where the temperature can rise to a very large value, and then it can lead in melting of the or failure of your heater, that is the point E. And sometimes you also want to know what is the minimum heat flux that you can achieve. Basically in a controlled heat flux experiment, when you are reducing the heat flux, you reach the minimum value D, and then below that it will come back to your the beginning of the nucleate boiling, and then back into convective natural convective boiling. So this is called the Leidenfrost point. So anyway, so anywhere between C and E is your film boiling. So initial part from C to D is called the transition boiling, where you have both convective effects. There are some vapor bubbles still nucleating, and in film boiling you do not see any vapor bubbles, they are all completely coated by a very thick vapor blanket. So you see, this is the snapshot of what happens in a film boiling. You can see that this is your heater, the black one here, and there is a very thick vapor blanket, and if at all there are any vapor bubbles, they are nucleating from the interface of the vapor and the liquid. So they are not happening right at the surface of the heater. Okay. So this is typically how the image looks, and as I said, if you do not stop at E and then you do not try to reduce the heat flux, it is going to cause the burnout, because the excess temperature exceeds the melting temperature of your heater. Okay. Now coming to important correlations, So, you need to understand the correlations to predict heat flux in nucleate boiling, because this is the most effective boiling regime. So, the most important correlation was given in 1952 by Professor Rosenau at MIT. Even now we have labs named after Professor Rosenau there. So, he did a lot of experiments on nucleate boiling, and he proposed an experimental correlation for predicting heat flux as a function of the fluid properties and the heater surface temperature. Okay. Now, whenever you come across boiling or condensation, usually the temperature is not given as some T minus T ambient, but it is T minus T saturation, because saturation temperature is the reference, because otherwise it does not make sense to talk about boiling or condensation if you are not considering saturation temperature, right. So, these are all thermophysical properties of the fluid, like density of the liquid, density of the vapor, surface tension, the latent heat of vaporization, heat capacities and so on. There are a couple of constants. So, this is not the best correlation to describe nucleate boiling, because this is an empirical model, and you see there are couple of coefficients now which is doing the job of this empirical model, which is the CSF, which is an experimental constant that depends on the type of surface and the fluid that you are using, and this exponent n, which is an experimental constant that depends on the fluid. Okay. Now, when Rosenau did this, of course he did it thoroughly, he did for a very wide range of heater and fluid combinations, and you can see that he has changed for example water with copper, and even within copper you have different types of surface roughnesses. As I said, your boiling process depends on the roughness of the surface. So, you used a polished copper versus something scored, which means it is more rough. So, and then for each of these cases he has deduced what is the constant CSF and the exponent n. So, like that he has repeated with different liquids, you have water, we have N-pentane, we have benzene, ethyl alcohol, isopropanol. So, these are all, water of course has a relatively higher surface tension. If you go to all these refrigerants and alcohols, you have very low surface tension fluids. So, he has been able to therefore not only change the working fluid, but also the nature of the material of the surface and the surface roughness, and he was able to deduce these values of CSF and N accordingly. And of course, if you look at the properties of water, they also change with temperature, right. So, depending on, so therefore the question is, what is the temperature that you use? Generally we use some kind of an average temperature between the heater and the saturation temperature. So, we use all these properties at an average temperature, which is basically calculated as Ts plus Tsat by 2. Okay. So, for example, surface tension of water decreases dramatically as you go to higher and higher temperatures. The other important correlation that was also later added on was the correlation for predicting the critical heat flux. So, this is something that you need to know before you start designing anything with boiling, because first thing you should know that you should not exceed this critical heat flux, and therefore the knowledge of critical heat flux is very important. And you can see that this critical heat flux correlation, it does not depend on the fluid and heater combination, unlike your nucleate boiling correlation. So, this depends mostly on the thermophysical properties of the fluid, and there is one coefficient called CCR, which is an empirical coefficient, and that depends on the type of geometry of the heater. So, it is not the same as the CSF that you had before, because that depends on the surface to the fluid combination, but the CCR depends only on the geometry of the heater, whether you have a flat heater or a cylindrical heater or so on. So, therefore, for flat heater you have a value which is like 0.149, if you have a cylindrical heater it is about 0.12 and so on. Apart from that, you can estimate the critical heat flux from only looking at the thermophysical properties of the fluid. Okay. And later of course people wanted to also look at what is the correlation for predicting the minimum heat flux, which is called the Leidenfrost point. So, a person called Zuber, he was able to successfully derive the expression for that as well, and that is also correlated as a function of all the fluid properties. Okay. And finally, film boiling, of course, you do not want to operate your device in this regime, but people wanted to know if you have only a pure vapor film blanketing the heater, what happens to the heat transfer performance. So, they have come out with a very nice correlation for film boiling. Now, this correlation, you may be surprised, it is not actually developed for film boiling, but for film condensation. So, the same film condensation, because in a condensation what happens is, so now in a boiling case you have a vapor, this is your heater, and the heater is coated with vapor blanket. Now, in condensation, of course, you are deriving the condensation when you have gravity. So, you have a cold plate and then you have a condensate liquid film. So, this is a liquid film condensate and this is the vapor. So, this is exactly opposite. Okay. So, adjacent to the plate you have a liquid film instead of a vapor. So, people derived this expression, this is called the Nusselt condensation theory, film condensation theory, and the same correlation was exactly used for film boiling by just tweaking the coefficients to the C film. And of course, swapping. So, in condensation the saturation temperature is basically above the the temperature of the surface. Here it is the other way, the surface temperature is above the saturation temperature. So, therefore, we use the correlation from film condensation in film boiling, except that the coefficient is tuned specifically for film boiling condition. And one more thing you have to keep in mind is, it is not just only boiling which is causing the improvement in heat transfer rate in film boiling, but it is primarily radiation. So, as you go to higher and higher heat fluxes, the contribution of radiation becomes very important. Therefore, if you do not account for radiation, your correlation to predict the heat flux in film boiling will be grossly underestimated. So, therefore, you take the contribution from film boiling from this correlation which comes from film condensation, and then you do a weighted average. So, 3/4 of your heat flux coming from radiation has to be also added to that, and that will give you the complete correlation for the film boiling, which considers both the boiling and the radiative effects. Okay. Just a couple of minutes before we conclude this lecture. So, you all understand by now that what is controlling pool boiling is how do we cause the nucleation sites to, how do we influence the nucleation to happen, and nucleation happens at a very small scale of the order of microns or even nanometers at the heater surface. And then if you really zoom in to using a microscope or using an SEM, you will see that this roughness is completely arbitrary, right. So, you do not have any clear control unless you specifically fabricate the surface yourself, either polishing it or making it very smooth or controlling the roughness with a grit paper, sandpaper, and with a specific roughness coefficient and so on. So, therefore, but people slowly realize that most of the later experiments, they were not able to get a very high quality of repeatable or reproducible set of boiling curves. Okay. The same boiling curve that Nukiyama gets shows here, it is obtained with copper as a heater, and then you have water. Now, if I do the same experiment with the copper that I have, and if I change the roughness of this copper, so I slightly get a deviation from this boiling curve, because again, as I said, the nucleation will be influenced by the surface roughness. So, therefore, the nucleating cavities are basically controlled by the surface roughnesses, and if I am not very careful in maintaining either a completely smooth or polished surface, so I can completely change the nature of these boiling curves completely. So, therefore, people also use this to their advantage. One reason is people thought that already you are having a very high magnitude of improvement in heat transfer coefficient. Over and above this, if I now alter the nucleation sites by changing the local roughness, I can improve this even further, right. So, therefore, they have done lot of experiments where they were able to enhance the heat transfer in pool boiling by changing the nature of these surface structures. For example, people are looking at porous structures, where these pores have a very specified void fraction or porosity, which can control these nucleation processes. And people were also using fins or micro fins or mini channel fins to look at how the nucleation is influenced. In fact, in our own lab we have done some pool boiling studies on using mini and micro channel fin surfaces, and these are some of the foil temperatures that we get when we use the infrared camera at different heat fluxes. For example, the top one is heat flux of 8 watt per centimeter square and the bottom is 85 watt per centimeter square, and we see that the nature of nucleation and surface temperatures are quite different when we use mini channels, for example different types of mini channels as opposed to a conventional flat heater. And in fact, if we use mini channels, this mini channel is having a dimension which is slightly larger size of mini channel, we find that we get a much lower surface temperature than what we get with a conventional flat heater. So which means the heat transfer coefficient is even improved by using this kind of surfaces where we have micro channels or mini channels. So the main reason for this is from what we did was either they are attributed to added surface area. So this is a surface area enhancement effect primarily, but apart from that if you reduce the size of these mini channels or micro channels, you can also enhance the nucleation sites. The nucleation site density can be improved and they can control the nucleation site density by in fact reducing the size of these channels, and therefore that also is another mechanism of improvement of these nucleate boiling regimes. So these are some of the images that we have, and you can see that as we increase the heat fluxes, A, B, C, A is the flat surface, B is one type of mini channel and C is another type of mini channel. We see that in flat heater you see it is transitioning to a very large bubble very quickly, whereas the bubbles are much smaller and more controlled when we use the mini channels here. So we have also seen the effect of these mini channels on the departure diameter which I was talking about and bubble departure frequency, and as you can see the bubble departure diameters are slightly smaller when we have the mini channels, which is good because that means it is promoting more smaller bubbles, and the bubble departure frequency is also slightly higher because more smaller bubbles of higher frequency is actually more conducive for maintaining the nucleate boiling regime. Well, I think with that I conclude this first presentation on pool boiling. So we will take a break for 5-10 minutes and come back and we will quickly look at condensation before we go into flow boiling. So, yeah. So that is like an equivalent spheroid that we assume. So we equate it to spheroid with the same volume and then we calculate what is the equivalent diameter, because these bubbles are not perfectly spherical as you can see here from this image. So these have some kind of a prolate kind of a shape. So it is like a prolate spheroid, okay, or a ellipsoid, whatever you want to call, and then we equate this volume to an equivalent spheroid and get the equivalent spherical diameter. So this is very standard practice actually. But if you apply for example an electric field at the top, this elongation can become very large and there is a deviation from its spherical nature. We also measure that extent of departure from its spherical shape and we have to look at it. But in most of the cases under normal earth gravity without any external electric field, it retains more closely to the spherical shape when it departs. And of course it also depends on the wettability of the surface. So if your surface is basically less wettable, like if you have a hydrophobic or a super hydrophobic surface, this angle will be much larger, okay. Whereas in a highly wetting case, you will see like this is a case where it is highly wetting. So the liquid is able to form a smaller contact angle. If your contact angle becomes much larger as in a super hydrophobic case, then this elongation will become much more for that matter, because the contact angle will be much larger and this departure will become much more from the spherical shape, okay.